Dear students, today we will learn a concept called greedy design technique and one of an application of greedy design technique. So what do you mean by a greedy design technique? Greedy design technique means where you try to decide on a particular way of solving a problem and you go ahead with that solution itself, right? So one of the application of greedy design technique is Prim's algorithm. So what does a Prim's algorithm do? Prim's algorithm will produce a minimum spanning tree. So what do you mean by a minimum spanning tree? It's a subgraph of a given graph where all the vertices will be present and you try to visit all the vertices with a minimum cost, right? So you can notice on the right side that I have given a graph where you have 6 vertices with all the vertices being connected with edges and all these edges are associated with some weights. Now using these weights you can know the distance traveled from one vertex to another vertex, right? So there is another criteria with Prim's algorithm where you go on connecting the vertices starting with one vertex, right? So when you are connecting one vertex at a time, you see that you take only minimum weight and it does not form any cycles, right? There should be no cycles when you are connecting those vertices. So we call this as acyclic subgraph. Okay, right? Now let's apply Prim's algorithm where you explore all the vertices with minimum cost. You can start from any vertex as a source vertex. I'll consider A as my source vertex. From this source vertex, I try to find all the adjacent vertices and out of those adjacent vertices, I try to find the minimum cost. So you can see B, F and E are the adjacent vertices for A. The distance traveled from A to B is 3, B to F is 4, A to F is 5, A to E is 6. Out of this, A to B is minimum. So I'll connect, So I'll connect A to B with the distance of 3. Now I have to explore other vertices with minimum edges. So I can see A to E is 6, B to C is 1, out of which B to C is minimum. So I'll connect B to C, right? Now you have to find adjacent vertices to A, B and C, explore in such a way that you get a minimum distance. So out of this, A to B is explored, B to C is explored, so we are left with F, which has a minimum weight of 5. So I'll explore F with a minimum weight of 4. Right? Now you have to see what are the other vertices which you need to explore. So A, B, C, F is done. We are yet to explore D and E. Right? So now find out C to D is 6, F to D is 5. So out of this, which is minimum, F to C is 4, which is minimum out of these 3. But if I connect F to C, it will form a cycle. And what is our intention? See to that no cycles are formed. So we do not include F to C. We can include F to D. So F to D would be 5. Right? Now how many more vertices are to be explored? One more vertex. Now you see the adjacent vertex to E. So A to E is 6, which is maximum. F to E is 2, it is minimum. D to E is 8. So F to E can be explored with a minimum distance of 2. Now you can see that we have obtained a subtree where you have all the vertices what is available in the main graph. So we have obtained a subgraph with minimum distance that will be traveled to all the other vertices. Now when we say minimum spanning tree, we also need to find the total cost of this minimum spanning tree. So now total cost would be the distance traveled. So it will be 3 plus 1 plus 4 plus 5 plus 2. So what is the total now? 3 plus 1, 4, 4 plus 4, 8, 8 plus 5, 13, 13 plus 2 is 15. So this is our minimum cost spanning tree. Any doubts? Thank you.